Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
I'm Devin.
And in studio with us we have Rick. And Rick, if somebody needed to get a hold of us, what would they need to do?
For math homework help, call in Bakersfield 636-4357, toll free 1-866-636-6284, email dothemath@kern.org. We're online at dothemathonline.net. And on social media, Facebook, Instagram, Twitter, and YouTube.
Well done. A lot of different ways to get a hold of us, aren't there?
Yes.
As a matter of fact, we have an email question we'll be addressing later on. But first, before we get going, where do you go to school and what grade are you in?
I go to Stockdale Elementary School, and I'm in 5th grade.
How's 5th grade going?
It's going pretty good.
Yeah. How long have you been at Stockdale?
Since kindergarten, so 6 years.
So you're pretty used to the place.
Yeah.
If there was one thing, so let's say they go, all right, you know what, you guys are going to be able to go back to school in a month or whatever it is, all right, or whenever it happens to be. And they said, Rick, it's been a while since you guys have been back. We're going to change one thing about the school, and you can name it. Is there anything that you think you might change about the school?
Like maybe we're going to, in lunch, we're going to sit far apart a bit.
Okay, so you would take up with that, right?
Yeah.
So you go, all right, we're going to, in lunchroom, we're going to make sure we have our space between us.
Yeah.
That way we can still get back to school.
Yeah.
All right, very good. Now, it's my understanding that you're working with fractions in class right now, right?
Yes.
All right, so what I want you to do is with Devin, you guys are going to just do a simple addition problem right now with some fractions, all right?
Okay.
So head on over to the board. You and Devin are going to come up with a problem and then explain to Devin how to best solve it.
Now,
Okay.
in all transparency for our audience, I just want to be clear. We had a conversation before the show. He was very clear. It was very clear. Whatever we do, we're not adding fractions with a denominator of 11. He
Right,
says
no
we're
11s.
We're going to shut that down right ahead. I'll say, if I see an 11 as a denominator, I am walking offset.
What about in the numerator?
I think that's fair. How about 11 twelfths is going to be one of our fractions.
Sure.
So we have 11 twelfths. Go ahead and put that down. And for the second one, let's make it a little bit lower on the denominator scale. So we're going to add, how about 3/5? So talk us through how you would add these two together.
So you would find a common denominator first between 12 and 5. So if you do 12, 24, 36, 48, and then 60, that's like a number common with 5.
So 60 is a number that has the common factors of 12
Yes.
and 5. And what's interesting is you didn't call it the least common denominator. I think a lot of people feel like they're kind of pushed towards that. But as long as it's common, it doesn't matter if it's the least common denominator. And you found that quickly by counting by 12 5 times, essentially multiplying 12 by 5. When you multiply two numbers together, you get a common multiple that has both of those values as factors. So 60 is going to be our common denominator.
Yeah. So I'm gonna.
So we're eliminating, we're removing just kind of temporarily the previous denominators. We recognize that there was a 12 right here and a
Yes.
5 here. The common
Yeah.
denominator is 60, but we still have these numerators to work with, don't we?
Yes. So since 12 was multiplied by 5 to get 60, we also have to affect the numerator by multiplying by
So
5.
we're going to find an equivalent fraction to 11/12
Yes.
where 60 is the common denominator. So we
Yes.
would do that with 11 as well?
Yeah.
Okay.
And it would be 55.
So that's equivalent to 11/12, 55/60ths, okay?
Yeah. And then you would do the same over here. So you have to multiply 5 and 12 to get 60. So you have to multiply 3 and 12, which will be 36.
36. So we went from adding 11/12 and 3/5 to now adding 55/60ths plus 36/60ths.
Yes.
We're able to add these now that they have a common denominator, correct?
Yes. And it will be 91/60ths.
Now, 91/60ths by itself, yeah, that is absolutely on point. Our solution, when you add those two fractions together, is 91/60ths. Some people like to go further than that and do something with this. There's not a lot of, some people like to call this an improper fraction because the numerator is greater than the denominator.
Yeah.
I don't see there's anything wrong with that. It doesn't change the value. But for some people, they prefer another way of representing that, correct?
Yes.
So what would you do anything with 91/60ths here?
Yes, I would put it into 1. 91 is 31 more than 60, so it will be 31/60ths.
So what you did was you represented 91/60ths as a mixed number.
Yes.
Which essentially what you did was you broke this down. You kind of deconstructed 91 as 60/60ths plus 31/60ths. And because we know that 60/60ths is equal to 1, we're
Yeah.
essentially saying that this is 1 plus 31/60ths, or 1 and 31/60ths. So
Nicely
there's our
done.
sum.
You guys did a great first problem right there. All right, we do have phone tutors available until 5:30 this afternoon, as we do most Tuesdays and Wednesdays throughout the regular school year. Time now for today's Math in the News. And this is going to be a rather quick one today, but we do need to, because yesterday we spoke about the Super Bowl and using Roman numerals. And the reason we need to talk about it again today is because it's been quite a feat, because Tom Brady, the quarterback for the Buccaneers, has won his 7th Super Bowl.
That's my guy.
But has been in 10 of them altogether.
Me and Tom go way back. I was there for his first ever preseason game.
Losing 2 of them, though, to the New York Giants. And he's still a little sour on that.
Numbers are
But
a
we let
little-
that one go by.
Sure.
But you can see Tom with the trophy right there. And there were a bunch of articles talking about the math behind what he has done. All right. So we can see right here. Now, this is if you randomly selected a player when he was drafted. So this is only out of the people that were taken in that draft year. Okay, not out of all the people that possibly played the NFL and things like that. So a randomly selected player would have a 21-year NFL career. Now, first of all, having a 21-year NFL career is a pretty big deal.
I believe that
All
the
right.
average is only about 3 for your standard NFL player.
Because
You get hurt.
especially, I mean, all the different positions, right?
Yeah.
Running backs get beat on, linemen are getting beat on, and all sorts of things happen to them every single play.
Kickers tearing hamstrings, you know how it
Right,
goes,
those guys last a little longer. But theoretical probability of that player winning 7+ Super Bowls, 2.3 in a million.
And that's if everything is randomized, right?
Right.
Like, let's say you're a member of one team and one team has to win a Super Bowl this year. It's not based on skill factors. It's literally
Lasting
a
that
ball
long
out of the
and
hollow.
having that many Super Bowls. So
Right.
you can see the decimal we've got, 0.00023% chance of doing what Tom Brady has done. All right. And then there was another one that I found. All right. We can see here 19 in a billion. All right. Chance of going to the Super Bowl
All right.
set and winning it. 7 times, and then let alone, so this was 55.
Yeah.
So he's been in 10 of the 55 Super Bowls, which is pretty remarkable when you come to think about it. And there are, I know, a lot of Patriots that have played in a lot of Super Bowls, but they weren't able to get to 10 because Brady moved on to teams. And we know we have a Buccaneers fan in the audience here today. We can see with his mask over there. So I'm sure that young man is pretty happy about that. But that is today's Math in the News. 636-4357 is that phone number. Do remember, you can also email us, dothemath@kern.org. We're going to get to that email problem in a little bit, but right now we have an opportunity to check out our Seed to Harvest program.
Hey, a little math in the real world. My favorite part of the show, I know it's yours. We are continuing our series of Seed to Harvest. All kinds of things like that happening here in Kern County. And one of the biggest parts of that is water. Now, someday you can tune into our 429-part series on water because there's a lot to do. But today we're just going to talk a little bit about the big picture of water. So I brought in my friend, Jeevan Muhar. Thanks so much for being with us today, Jeevan. Thanks. You are part of the Arvin Edison Water Storage District, is that correct?
That is correct.
Okay, and what do you do here?
I'm the district's engineer manager. We manage essentially the water supply, power contracts, and distribution facilities, and then obviously the workforce.
Right, so we have a lot of water and a lot of power to move that water around. And there's a lot of different agencies in California, or at least in the San Joaquin Valley, that do the same thing that you do. Can you tell us a little bit about what we're seeing here? This is north and that's south, is that correct?
Correct, and you got Stockton at the top of the page, so this isn't even the entire San Joaquin Valley. And here at the southern end of the San Joaquin Valley, here's Arvin Edison. We're tucked away here. The Tehachapi Mountains are here. The Grapevine going over to LA is just south of us here. So we are but a very small piece of the puzzle here. We're part of the east side service area from the federal government. The Central Valley Project is what it's called. We actually get our water from Fresno, Millerton Lake, San Joaquin River water. That water flows down the Frank Kern Canal, 152 miles before it even gets to our service area. Also in the valley, we've got a big west side of the valley, which is State Water Project for the most part. On the southern end of the valley, and then Metropolitan Water District of LA is a big contractor of the State Water Project. And then going north on the western part of the valley is more Central Valley Project District's federal water supplies.
There's so much going on, and we know that water is absolutely important for agriculture, especially in Central California. And there's just not enough readily available that someone can just scoop up off the ground, right? So there's all kinds of different ways that you can order water from up north, right? But then sometimes you have too much water, right? So what do you do when you have too much water? And that's a nice problem to have at Bakersfield.
Yeah, it is. And so our contract with the federal government is that of during the wettest of years, when the reservoir is essentially overtopping and about to spill, we get the largest quantity of water at that point in time. So during the wettest of years, we get a lot of water.
Okay.
And we take that water and we put it into our spreading basins. We've got over 2,000 acres of spreading basins that then percolates. That water will percolate from the ponds into the underground aquifer.
So you can save it.
So we can save it for another year, for those dry years.
Totally. Let's take a look at a typical year. I love this chart here because this is a really, really good information. This is the year when you had some wet times and some dry times. Can you give us just a real broad overview of what happened? This is in 2009, right?
Correct. So we started the year out pretty dry. We had to run our wells, our extraction wells, from the underground.
Okay.
So remember,
the black line is the wells, right?
The black line is the well. So remember, during the dry years, we don't have enough water. We've got to pull it back out of the ground.
Yeah.
Which we put in the ground years prior.
Sure.
And so we started out the year dry. We started to make the deliveries to our farmers. We've also got some return obligations to Los Angeles, and then in the other areas we're actually putting water into the ground. So the blue lines are actually our daily well fill extractions. The red lines are our imported water supply. And so what happened in late April, early May, the reservoir was too high and we had to evacuate the water. And we had to dump the water essentially into our ponds. We'd rather have that water in the summer,
Sure.
but we had to dump the water into our ponds for another year.
So the wells went down, and the water, you got a whole bunch more water, and you started banking it.
We started banking
And
it.
that's why you're here, right?
That's right.
There's so much more to see here, but this is, I think, the most important part. Tell me a little bit about this chart, because I think it's easy to read, and it tells us why you exist, right?
Absolutely. This is why we're here. This is our goal. This is stabilizing the groundwater levels. So as you can see in the actually going back to the 30s and 40s, the groundwater levels were dropping 6 to 8 feet a year. And in 1960, we got our water supply contract, we got our power contract, and we got a loan from the federal government to build our facilities. And you can see starting in 1966, when we first started making deliveries, we stabilized the water table.
And this is because you put water back in the ground. You take some out when you need it, and you put it back when you have too much.
And we took people off of groundwater as well.
Oh, there you go. Man, there's so much to talk about. I love this. Is a great way to visualize what you have done and why you exist. We want to know a little bit more about what's going on, and so I think we're going to see a little bit more technical side of this operation. Maybe even get outside and hear some water pumps running. So much to talk about. At the moment, I know there's more math to do back in the studio, so we'll head there.
All right, thanks for that, Scott. Always more math to do. And today we've got Rick, a 5th grade student from Stockdale Elementary, in studio with us, working on some fractions. You added fractions before, and one of your homework problems is to multiply now.
Yes.
All right, so here we go. 1 and 5/6 times 4 and 1/2. So you and Devin can take it away.
I'm always curious to see the different approaches students take when it comes to not just multiplying fractions, but when mixed numbers are involved. So talk us through what you would do here.
So you would multiply the whole number with the denominator and then add the numerator and then divide by 6. So if you do 1 times 6 plus 5 over 6, that would basically be like it. And then
Go ahead.
you would do the next problem, 4 times 2 plus 1.
So what you're doing is you're converting both of these mixed numbers into improper fractions that are equivalent.
Yes.
Okay?
So if 1 times 6 is 6, plus 5 would be 11.
Because what you're essentially saying with this fraction here is that 1 plus 5/6 is the same thing as 6/6 plus 5/6.
Yes.
So just like before when we added, we can get this to be equivalent to 11/6. So the same thing here, 4 1/2. If you think about 4 wholes in terms of halves, that's really 8 halves, right?
Yeah.
Because that's equivalent to 4, and then we're just adding one more half to that. And that's going to kind of give us a clue as far as what this is going to equal. So go ahead and kind of calculate out that improper fraction. So we have 11/6 times 9 halves.
Yeah.
So I'm curious to hear where you would go from here. Talk us through what comes next.
You multiply the numerator, which is 99. Then you multiply the denominator, which is 12.
So pretty straightforward calculation. Again, if you just leave it at that, mathematically that's equivalent to the product of those two fractions, absolutely. There are some that would look for a simplified version of this fraction. If we were going to simplify this fraction, what would be a common denominator that we could use just very quickly to see if we could simplify that?
8.
8. Why do you say 8?
Because if you multiply 12 and 8, it'll be below 99, but the closest.
Now, can you divide 12 by 8 and get a whole number as your quotient?
Yes.
So what does 12 divided by 8 equal? Now, we know you can subtract by 8, and you could multiply by 8 to get something larger, but can you divide 12 by 8 and get a whole number as the other factor?
I don't think so.
Okay, so then we have to reconsider 8 as our divisor to simplify by. Let me tell you about a rule of divisibility that's very helpful. And rules of divisibility are nice little templates to use in case you need to wonder if you can divide a number by something. So with 2's, for example, it's really easy. If it's an even number, ends in 2, 4, 6, 8, or 0, you can divide it by 2.
Yeah.
But there's something interesting about 3 families. So here's one way to know if you can divide a value by 3. Take a look at the digits that make up a number. For example, 12. If you add up the digits, for example, 1 plus 2, what does that equal?
3.
So if you end up with a sum for those digits that is 3 or a number divisible by 3, then you can divide this by 3. So because these add up to 3, we know we can divide this by 3. Let's check to see if this works up here as well. 9 plus 9, what does that equal?
18.
Now if you're not sure if you can divide that by 3, keep going. 1 plus 8.
9.
Can you divide 9 by 3?
Yes.
So you can divide 99 by 3.
Okay.
So let's see if we can simplify this by 3.
I think what he was trying to do is he was simplifying it into a mixed number, dividing. He was going to go 12 goes into 99 8 times.
Right.
That's where he got the 8 from.
And that still would have gotten us, that would have gotten us close, but we
Right.
would have had remainders. And we don't have
And then
time
I
for
see what you're doing here,
remainders.
so continue on, boys.
So let's see if we can simplify this by 3. 99 divided by 3 or 12 divided by 3. Which one would you like to tackle first?
99 divided by 3.
Good for you. All right, 99 divided by 3. What would that get us?
33.
33. Now, 12 divided by 3.
4.
So there are no more common factors between 33 and 4 because we know that the only factors of 4 are 1, 4, and obviously 2.
2,
And we know you can't divide 33 by 2. So 33 fourths. We could turn this into a mixed number, but right here is a simplified version of the original product we got. So we had a lot of steps along the way, but long version short, you converted these whole numbers into these, mixed numbers into improper fractions, and then use the skill of multiplying fractions across, which works. There's other models that show it works, but you got to this, and we can play around with it, turn it into a mixed number, simplify it, but this is the core of where we needed to go. So nice done, Rick.
All right, good job. All right, we're going to go to the phones right now. And Kelly, how are you this afternoon? Hello, Kelly.
Hello.
You're a 6th grade student at Old River, correct?
Yes.
And you're working on an equation?
Mhm.
Okay, as soon as you're ready, let's hear the problem.
Okay.
So you can just go right to the board and Rick, come on over this way a little bit.
Go ahead, Kelly, we're ready for you.
4 parentheses divided by x parentheses equals 2 bracket 3 parentheses x plus 2 parentheses minus parentheses 2x plus 4 parentheses bracket.
Whew, lots
Okay,
of
so once he gets it
parentheses.
written on the board, take a look at it and make sure it is the correct problem.
So I have 4 parentheses 2 plus x equals 2 brackets 3 parentheses x plus 2 minus parentheses 2x plus 4, close your brackets.
Yes, that's correct.
Okay, and what we need to do is we need to find the value of x, correct?
Mm-hmm.
Okay. Well, Kelly, we have a lot to handle here with the distributive property. The idea with the distributive property is that we can take a value that is outside of a set of grouping symbols, like parentheses or brackets, and then multiply that into everything inside of those. So to illustrate that very quickly, we can do that over here on the left side of our equation. We have 4 times 2 plus x. So So we're going to multiply everything inside this group by 4 on the outside. The 2 and the x. So we have 4 times 2, and that equals 8. But where a lot of people get tripped up with the variables is, well, how do you know what 4 times x is if you don't know what x is? Well, the easy answer is we just know we have 4 of something. So we're going to continue to use x and just say we have 4 of them. 4x. And we can do the same thing on the other side of the equation as well. But there's something interesting here. If you were watching earlier with Rick, we had a situation where we found a common factor. So what I'm actually going to do is I'm going to take a couple of steps back here. I'm going to take our 8 plus 4x and just kind of move that over to the side. I don't want to forget that this is equivalent. But if you notice, we're multiplying this side by 4. We're multiplying this side by 2. These big brackets here are very clumsy for us to play around with. I, for one, would love to get rid of them as soon as possible, Kelly. So I hope you'll be okay with this. I'm going to divide both of these sides by 2. If I do that, I get rid of this coefficient, which means I get rid of the big brackets. Now over here, I can divide 4 by 2. So now on this side, I have 2 times 2 plus x. And over here, I just have everything over here. 3 parentheses x plus 2 minus parentheses 2x plus 4. And this is going to get very interesting very quickly. We have a couple of things we can start to distribute here. I have a 2 that's going to go into 2 and x. So 2 times 2 is 4, and 2 times x is 2x. 4 plus 2x. I want you to remember that here. Now on this side, we have 3 times x plus 2. So 3 times x is 3x. And then 3 times 2 is 6. That's great. I have 3x plus 6 minus 2x plus 4. Another thing that can be very tricky and cumbersome to play with is when you have a negative symbol next to a set group of parentheses, right? Because sometimes we can get confused. We aren't sure whether we have to distribute that negative into everything. But let's go back over here. Let's play around with properties, because I know this looks a lot like a distributive property problem, but there's another property that can be very helpful with us. It's called the commutative property, but you've been focusing on this ever since you were in kindergarten and first grade. It's the idea that 3 plus 2 is the same thing as 2 plus 3. It doesn't matter which order you add them, they're still the same thing. So we can take 4 plus 2x, and if we switch them around, we've got something else. We've got 2x plus 4. It doesn't matter which order they're in, they're still the same. And now that I have that, I can take this, and I can add a 2x plus 4 to both sides. And that's going to eliminate it on this end, because these two negate each other and make a 0 pair. And now over here, we have 4x plus 8. We added all the terms together. We combined like terms. Mike, can you bring this up so I have a little bit more room to work with here? Because we're just about there, Kelly. This is a really fascinating problem. And whoever assigned these to you, I don't know your opinions of them, but give them the credit for giving you something to really play around with. This is going to be 4x plus 8 now. And we have 3x plus 6. The goal of any equation where we need to find the value of a variable is to isolate it, to get it by itself. And we're almost there. So what I'm going to do is I'm going to take 3x away from both sides of this equation. What that's going to give me is x plus 8 equals 6.
Now I can move it down just a little if you want.
We got one step left, because now, in order to get x isolated by itself, we need to remove this 8. And we do so, again, everything in an equation is balanced. we do so on both sides. We're going to subtract 8 from both sides. X is equal to 6 minus 8, or negative 2. It seems like a lot of work, and I know that seeing this can be scary because of what it entails, but all this is just one step at a time. And what's fun about a problem like this as we started off is that there's a lot of different ways you could approach it. But when you start to look for patterns, for things you could do to see where it goes, where you end up always ends back to the same place. Kelly, great problem. Thank you so much.
Nicely done, Kelly. And for your efforts today, you've got yourself a meal courtesy of our friends at The Broken Yoke. So congratulations on that. Hey, we do have phone tutors available until 5:30, but right now we do have another opportunity to go out and visit Scott and see how our seed to harvest is going.
Hey, Math in the Real World, we're still talking about water, and we need to know a little bit about what happens here in the Arvin Edison Water Storage District, about when all the water gets here, what do we do with it? I mean, you have some settling ponds, and we have some pumps, and we got all kinds of stuff, of which I know very little about, so I have, again, my friend Jeevan to tell me a little bit about what's happening. So overall, you get water from Millerton Lake, 152 miles, comes down, you got the water. What do you do with it?
So it depends. Is
Yeah.
it a wet year? Then
Yeah.
I'm putting water in the ponds.
Okay, yeah. So this is an overhead aerial view of the ponds, right?
Sycamore
And this is
spreading.
how the water can sink down back in the ground.
Correct. And we're standing right here.
Okay.
And you can see the scope of work here. I mean, that's our Sycamore Spreading Works, about 500 acres of ground that is in ponds. In wet years, we'll put it in the ponds. That water will percolate into the underground for another year. And then these little islands stretch throughout the Sycamore Spreading Works are extraction wells.
Gotcha.
which
That's where
then
these wells
bring-
come in, right?
Bring the wells the water out that we parked
Yeah.
earlier in the prior years, and then that water now is being delivered to the farmers.
Right. And this is not a random operation. You have a lot of data. You have a lot of data to make sure this is an efficient operation. So tell us a little bit about what we're seeing here, because you want to monitor your wells, right?
Correct. We monitor our wells every single day. We want to make sure this is our water supply for our farmers. And we want to make sure that we're on top of what's happening. And so in this particular graphic, this is today's snapshot of which wells are running in which section of the canal. The red bars are stop logs or check structures that hold water back in certain reaches of the canal. And then the blue bars is where all the water is coming into the system. Again, Sycamore Check is another key facility. This is the middle of the district, and everything north of here are all the wells that are serving the north side, and then south of Sycamore Check are the wells that are irrigating the south side for the most part. There's a lot of commingling. We've got surface water coming in on top of that to help meet the demand. And so that's every single day we track this information.
And some pumps are on and some pumps are off, and there's a lot of factors that go into that, right?
There is a lot of decisions, and a lot of it has to do with efficiencies. Some wells are less producers. Some wells are more expensive. Chris, can you go to the other graphic that shows the wells that from low to high, and not every well is created equal.
Yeah, that's
So we've got some wells as low as 2 CFS, cubic feet per second, all the way to some of our newer wells that we've drilled just recently, all the way to just over 7.5 CFS. So we have to manage that water supply on a day in and day out basis. We take water orders. Chris takes water orders from the farmers. We convert that and figure out what we need for the day based on what we got in wells, based on what we think we need from the surface water. Kind of just close that loop and figure out what part of the pie we got.
So many different aspects to come together, and they have to all make sure that the farmer gets the water, right?
Yeah, at the end of the day, we're here for the farmers.
That's right. That's right. Okay, super ignorant question, but I got to ask because I know somebody out there is wondering, how long does it take from the minute a farmer orders some water to the time that they can actually receive it?
So they actually have to order water 24 hours in advance.
Okay.
And we place our water order 24 hours in advance from Millerton if that's where we're getting our water supply from.
Right.
And however, we did relax some rules from the farmers. They typically used to have to take that water for 24 hours. We've built some facilities and tools for the folks in the field to manage that water less than 24 hours. We have volumes that we deal with essentially from day to day. And then we just divvy that water up based on their orders.
Yeah. So accommodating. I mean, hey, we'll get you water in 24 hours. If we have too much, we'll deal with that. We'll work with you. Gosh, man, these farmers are lucky to have you. This is pretty neat. We want to go out and see a little bit of the hardware that's going on outside, see what's going on with those pumps and maybe the ponds and, oh man, so much more to talk about. The moment I know there's some more math to do back in the studio, but we will be back to talk about more water issues.
That's right. Always a lot of things to deal with water, especially going from seed to harvest, all of that agriculture here in Kern County. We do have Rick in studio with us, a 5th grade student from Stockdale Elementary, working on some fraction problems. So, are you ready, young man? I think we're going to go through 1 or 2 of these right now.
Yeah.
So you've got Beth's Monday schedule up on the board, and we're going to take a look at some of the problems right here, and we'll just do one at a time, see how far we go right now. All right? So what fraction of Beth's Monday class does ballet represent?
2 1/2.
Now, we know that this table represents kind of her dance schedule as well as some of the hours that are put in. And your initial answer was that 2.5, could you go back to the problem? What fraction of
What
the day?
fractional part is ballet
So you
to the
saw-
whole schedule?
You saw fraction and you saw ballet and you went to 2.5. But let's go back to what the question is asking. What fraction of the entire day is represented by ballet?
1/5.
Now, it would be 1/5 if all of these were the same time frame. If modern dance was 2 and ballet was 2 and jazz was 2. Let's talk a little bit about what each of these represents, right? So one column is the dance class that she takes, right? And then another column next to it represents the number of hours she spends in that class on Monday. So let's talk a little bit about this, okay? How many hours does she spend in modern dance?
2.
2. So 2 hours in modern dance. How many hours does she spend in ballet?
2 1/2.
2.5. How about jazz?
1 1/4.
Okay. Now, character class. How many hours does she spend in character class?
1 1/2.
And then for strength training, which maybe doesn't have to do specifically with dance, but helps prepare the body, how many hours does she spend in strength training?
3/4.
3/4. Now, there's a couple of things to consider. Are all of these classes the same length?
No.
No. So they each represent a different portion of the day. Now, another question I would ask you is, how long is this day? Now, we're not going to worry about things like breaks and lunchtime, right? So, if we just add up the hours of class she has, if we just consider all the class she takes, how many hours is she in class for the whole day? Or how would we figure that out?
By adding all of them.
Now, do you have a strategy for adding a whole bunch of fractions and mixed numbers like this?
Add the whole numbers first.
Okay, let's do that. Go ahead and take care of that. Add all the whole numbers first.
6.
Okay, so 2 plus 2 plus 1 plus 1. Nice. So what's going to be our next step?
Add the fractions that don't have whole numbers.
Okay, so we're just going to add the fractions themselves now, right? Now, I don't know if you see these with the fractions that I see, but some of these fractions go together very nicely. So talk us through that.
In character and ballet, it's 1/2. There's 2 1/2s, which makes 1.
Okay.
And then in strength training and jazz, it's 3/4 and 1/4, and they make up another 1 whole.
So we have 6 and 1 and 1. If we add all these together, how many hours is the whole day?
8.
8. So we have an 8-hour day, which is great. So I'm going to represent that. If our whole is 8, let me ask you this. If our whole is 8, then what part of the fraction would that be? Would that be the numerator or the denominator?
Denominator.
It would be the denominator. So let's go ahead and put together a fraction with a denominator of 8. Awesome. Okay, now the key is the numerator. If the question is asking us what fraction of the day is taken up by ballet class, what's our numerator going to be?
64.
Ooh, where'd you get 64 from?
Oh wait, ballet.
Yeah,
Um,
ballet. because the numerator represents the part
16.
of the fraction. Now, where do you get 16 from?
Ballet, 2 hours, which is 2 times 8, so it's 16.
So let's think about this. Out of an 8-hour day, she spends 16 hours in ballet. Oh, I don't know if that sounds right.
Well, 16 out of 8, 2 hours.
So 2.5 hours is the amount of hours she's spending in ballet,
Yeah.
which gives us kind of a problem, because what that tells us is that 2.5 is a numerator. Can you have a fraction in a numerator?
No.
You could, but it's not very clean. So let me ask you this. Can we create an equivalent fraction?
Yes.
If you double this and then double this, maybe you get something equivalent. So let's do, and the reason I'm doing double is because our denominator here with this mixed fraction is 2, right? So 2.5, or I'm going to represent this as an improper fraction, 5 halves, okay?
Okay.
If I multiply that by 2, I end up with 10 halves, or what?
5.
5. And the reason I'm doing that, again, I want to make sure I don't have a fraction in my fraction. I don't want, it's what it's called a complex fraction. You can have those down the line, but you know, 5th grade, who needs this right now? So we're going to have a 5 here. But whatever I do with the numerator to get an equivalent fraction, I have to do with the denominator.
Yeah.
So 8 times what? If I multiply this by 2,
8 times 2.
great. So 8 times 2 is?
16.
So here's what this means. 5/16 of the entire day are spent in ballet class. And that makes sense because it's a little more than a fourth, right? If we know that there's 8 hours, 2 out of 8 would be 1/4, right? So this is a little more than that because we know that 4/16 is equivalent to 1/4. So 5/16 of her day on Monday is spent in ballet class.
Nicely done with that problem right there. Hey, we do have phone tutors available until 5:30, as we do most Tuesdays and Wednesdays, but even bigger news than that, the Mars rover Perseverance will touch down on the surface of the red planet on Thursday, February 18th, around noon Pacific time. Its mission, in part, is to gather Martian soil for testing as scientists search for an answer to the question, has there ever been life on Mars? We'll do the math as counting down the days to the big STEAM event with special coverage. We go behind the scenes to see how this mission came together and what we can expect from Perseverance once it does land on Mars.
This, in a sense, is kind of a holy grail for us.
We're in the outback of Australia because this is some of the oldest convincing evidence for life on Earth. And the Mars 2020 mission and the ExoMars mission are going to be looking for signs of life in the ancient past on Mars. And it was a great opportunity to bring the mission teams here to really see for themselves what we're talking about when we're talking about ancient biosignatures.
This part of Western Australia, called the Pilbara specifically, it's really absolutely a mecca for understanding the record of life on Earth. This is one of the most important places on the planet, geologically speaking.
Members of the science team came out here to look at some of the oldest rocks that are on Earth. These rocks are anywhere from 2.5 to 3.5 billion years old, about the same age as the rocks that we're going to find on Mars. And what's very special about them is they have evidence of the earliest life on Earth.
The rocks you see right in front of me here, these wrinkly layered structures that we call stromatolites. Structures like this actually represent fossilized microbial mats.
A microbial mat is actually a structure preserved in the rock made by communities of millions and millions of microorganisms.
Basically fossilized pond scum in a sense. Microbes, bacteria living in a shallow water environment. And we believe that if life ever existed on Mars, it would have been purely microbial.
And those are left behind in the record that are very distinctive. And so we've been showing the NASA and European Space Agency scientists the details of what those textures look like.
When we say with Mars 2020, we're seeking the signs of ancient life on Mars, this is precisely the kinds of signs of life that we'll be seeking.
I've learned to be a kind of a Martian to be in a harsh environment. My comfort zone is the laboratory, but you know, here I can see that this is the real stuff. It's not just simulating stuff in the laboratory. This is a real good training for us.
It was really important to get the science team out here, and speaking for myself, I had seen pictures of rocks like this, and they didn't really convince me that they were the product of life. And when you see them up close and personal, it really tells the story that this was once life. And that's something you just can't get if you don't go out and look at rocks like this.
You can study it, you can read about it, but there's nothing like the practical experience of trekking around in the desert and really trying to think about, as we land our Mars rovers there and we look at the images provided by our sensors, how do we interpret that and follow the clues to try to find the kind of evidence that has been unearthed here in Australia.
Could Mars ever have supported life? And then to take the next step, did Mars ever host life?
We're just smart enough now about Mars to ask the really hard questions.
Well, Perseverance touches down on the Martian surface Thursday, February 18th around noon. Live coverage of this special STEAM event begins at 11:15 a.m. right here on KETN, a service of your Kern County Superintendent of Schools office. So that is something everybody is looking forward to, and I know you are as well, right? You've got your sweatshirt on with NASA. What kinds of stuff have you learned right now, or are you looking forward to?
The Perseverance Mars rover.
Yeah, so that's going to happen next week.
Yeah.
So have you learned some things about it already, or you're going to do some more afterwards?
Do some more afterwards.
Do some more afterwards. All right, well, good. You know what? It'll be a big day coming up next Thursday.
Yeah.
Have you ever done puzzles?
Yes.
Yeah, all right. What are these right here?
Toothpicks.
Toothpicks, right? And what kinds of shapes are they making?
Squares.
Squares. How many squares do you see right now of any size?
6.
Can you show me the 6 of them? Like point to them?
1, 2, 3, 4, 5, and then this whole thing 6.
Excellent, good. I'm glad you were able to recognize that those 4 squares of smaller size make one larger square, right?
Yes.
Okay. Now, what I'd like you to do is you're going to take away some toothpicks, and you're going to leave a certain number of squares. All right? So what I'd like you to do is remove 3 toothpicks. You can only remove 3, but there must be 5 squares left. All right? So go ahead and whatever you're thinking about, you can also talk about to make it a little bit easier for those viewers at home.
Now, does he get to move them?
Well, he doesn't get to move them. He's doing, so I see what he's doing. You're moving them, which is fine, because that makes 5. But instead of moving the toothpicks, we want you to totally remove them.
Okay.
Okay, and you have to remove 3 of them.
Which 3 are you thinking about right now?
This, this, and this.
Okay, so
if you take those 3 away, what happens?
You have 3 squares.
All right, and how many do we want?
5.
5. So let's put those ones back.
now when you saw 6 squares, you saw that largest one, right?
Yeah.
Which means you need to find a way to take away 1 square using 3 toothpicks. How might you do that?
All right, so count them up. How many squares have you got now?
3.
3. All right, so why don't you set those back up again? So what I want you to do, shift over this way and take a look at it. Maybe looking at it in a different direction might help you out a little bit. A different perspective. There you go. So you removed 3. Now show me the 5 squares. Can you point them out? Well, you're going to take that one away because you're correct so far. Do you see 5 squares now?
No.
Sure. Point them out. Point out the ones that you see readily.
Oh, wait.
There you go.
1, 2, 3, 4, 5.
There you go. Perfect. So you did see it. Now, the reason you saw maybe that big one is when you were on the other side of the counter, you saw that. And then changing your perspective, you were able to see how to take away the 3. And then for some reason, it took a second to see that larger one again. So set up that last square right there. And we're going to do another problem right now. So now what I'd like you to do, and you can start here, you can start there, wherever you want, is take away 5 to leave 2 squares. Okay, you're going to take away 5 toothpicks to leave 2 squares. How many have you got there? You've got 5 taken away, and do you have 2 squares?
Yes. 1, 2.
Very nicely done. All right. So by looking at things at a different perspective, was it a little bit easier
Yes.
to do it that way?
Yes.
All right, good. Why don't you set those up one more time? And I've got a final problem for you and Devin to work on. This is one that you guys were working on a little bit earlier. All right. But I'm going to have you guys go back to the board and work on this problem again. It's just another way to do it where once you get good at simplifying early on in the problem, sometimes you can cut it down on time. All right. So head on over to the board. We had 11 over 6 times 9 over 2. And what I'd like Devin to go over with you is how you can simplify this before you multiply and then simplify after.
Now, we can think about this. If you come back to when you were multiplying, what you essentially did was you took these 2 factors and multiplied them by these 2 factors. So it ended up being 11 times 9 as your numerator, and then 6 times 2 as your denominator. Now, what's interesting about all these properties we've been talking about today is I feel like sometimes we lose sight of what they can do for us. We have a property in multiplication just like we do in addition as well, the commutative property, where we can switch around values and it still gets us to the same thing. And then we can also deconstruct fractions just like we did when we were breaking them apart to add their little pieces together to make mixed numbers. So we can also, I'm going to argue this, and you tell me if I'm off base here. We can argue that if we switch the position of these 2 factors, but keep the structure the same, 11 times 9 over 2 times 6. Rick, would this still end up with the same value as this?
Yes.
Okay. Now, if that's the case, then we can also break these apart as 2 separate fractions. So we have 11 halves times 9 sixths. Now, if we multiply these together, Rick, would this end up with the same product as these fractions that we started off with?
Yes.
So
And you guys have about a half a minute.
what we can do with this then is look and see if we can simplify any of these fractions. Can we simplify 11 halves?
No.
But could we simplify 9 sixths?
Yes.
What could we divide both of these by?
By 3.
So let's do that. 9 sixths is equivalent to 3 halves. Now, 11 thirds times 11 times 3 is?
33.
And 2 times 2 is?
4.
Didn't we get 33 fourths last time when we multiplied? And now we don't have to reduce any further or simplify.
Yes.
We're already there.
Nicely done. That's what I wanted him to see.
There we go.
So if you just when you look at the original problem, you could look at the 6 and 9 as cross products, and you could already look. You can divide each of those by 3, and you can solve that a little bit quicker sometimes. Anyway, for your great effort today, you've got yourself a meal courtesy of our friends at Broken Yoke. So nicely done on that. Hope you have an opportunity to enjoy a great meal over there. We do have one last opportunity to go visit with Scott and our friends and see how everything is going from seed to harvest.
Math in the real world. Jeeva, we're outside. We saw inside in the control room where that water is going, right? And all the pumps and everything. And here we have a pump behind us. Tell us a little bit about what is happening back here. How powerful is this pump?
Sure, so this is a 300 horsepower motor pulling about a 3 cubic feet per second pump of the water that we percolated in these ponds that's in the underground, and we're lifting that about 350 feet.
Right. So this isn't the time of year that your ponds are full, but they've had water sinking down, and now you're pulling this water out of the ground, right? Putting it in the canal.
Putting it in the canal, and it's going to now get distributed to all the farmers that have ordered the water for the day.
Right. So how much power does this thing take to run? I mean, that's a big pump.
Yeah, so the transformers are up top. We have our own distribution system for transformers, but this is 100 kilovolt amp transformers. So 3 of those for 300 kilovolt amps.
Wow. Okay, so we got the water out of the ground, going in the canal, going to be distributed to the farmer.
Correct.
Let's go see what happens next.
Let's go.
All right. Even the water's in the canal, right? It's to the farmer. Here we are in the field. The water's coming out of the ground. What happens next? You have to bill for this, right?
Sure.
Yeah.
So this particular water user has called us 24 hours in advance.
Right.
And he's told us, I need 1,350 gallons per minute. And we do a conversion. We actually deal with a different unit, which is cubic feet per second.
Right.
And so we actually turned his turnout on for today at 3 cubic feet per second, which is what he wants. And that now is irrigating his carrot crop field. We'll take that 3 cubic feet per second. If you irrigate for 24 hours, that's roughly, you double it. The conversion is double. So he would take 6 acre feet. Cubic feet per second for 24 hours is 6 acre feet. And we'll take that 6 acre feet, and that's what he gets billed on, is the volume that he's taken.
Wow. A little bit of math out here. Look at that. It's not just growing carrots. It's not just water trickling from here to there. Definitely some math happening. Oh my goodness. So there's a meter here, there's a meter there, and then of course, once the water is in the canal, you gotta get it to the next guy, right?
Correct.
You gotta pump it different directions.
Correct. So we are in the foothills. So a big part of our operation is pump stations and pipelines to get it to the next level and up the hill. And so this pipeline system is pumping uphill to the next set of growers that are on that particular system.
And I like this part too because it really lends itself well to where we're going next, which is learning about nutrients, learning about diseases. We're going to get back with Jeff Rasmussen, but gosh, Stephen, I'm so grateful for your time. We have the famous Do the Math tile for you today. We don't have t-shirts and hats to do the math. We have a tile, so we'll hand that off to you. You can put that in the office. Thanks so much. We learned a ton about water today, and we are going to wrap it up now. Back next time. Oh gosh, so much more to learn about seed to table.
All right, thanks for that, Scott. We do have phone tutors available until 5:30. We want to say thank you to Kelly phoning in this afternoon from Old River Elementary. And a big thank you to, you know what, Rick, you have done a lot of work today.
Yes.
Did you learn a little bit today?
Yes.
Good, I'm glad you did. I'm glad that Devin and you were able to work together and find some different ways to solve those problems. Did you have some fun?
Yes, totally.
Even better. I'm glad about that as well. Hey, until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.